Hello everyone, welcome back. Today we will be continuing our discussion on the energy balance for closed systems, specifically now for the ideal gas process calculations. So in our previous meeting, we have discussed or solved sample problems involving steam for steam problems in the closed systems. So now what about ideal gas calculations for ideal gas closed systems? So recall our energy balance for closed systems, du is equal to dq plus dw, and dw is equal to negative pdv, and work is equal to negative integral of pdv from v1 to v2. Now, how do we evaluate delta u and w? So previously, we have used thermodynamic property tables to evaluate delta U and W. So W using our specific volumes from the steam table and the specific internal energy to get delta U. However, we can also use property relations and equations of state in order to quantify the changes in internal energy and the total work, and thus from these two we can get the total heat transfer for many systems. So now what are equations of state? Equations of state are equations that relates pressure and or molar specific volume and or temperature of any homogeneous fluid in equilibrium states to each of these intensive variable properties. So one of these three properties may be solved as a function of the other two. So we can have an equation of state P and V to give temperature, or P and T to give volume, or T and V to give pressure. And the simplest equation of state that we have is the ideal gas law. PV is equal to RT. And the assumptions here is that as pressure approaches zero, so at low pressures, we have no molecular interactions, and the volume of the molecules are much less than the volume of the gas. So for an equation of state, we can have PV over R is equal to T, or we can have P is equal to RT over V, or we can have V is equal to RT over P. So we have T, P, or V as functions of the other two intensive variables. Now, recall for internal energy that the internal energy of an ideal gas is dependent only on the temperature. Thus, U is a function of temperature only. We can now define enthalpy as H is equal to U plus PV. And for ideal gases, PV is equal to RT, thus H is equal to U plus RT. Meaning, internal energy is a function of temperature only, and for an ideal gas, both internal energy and enthalpy are functions of temperatures only. So now, how do we relate internal energy and enthalpy to temperature? In order to do this, we define our heat capacities. And there are two types of heat capacities. One is the heat capacity at constant volume Cv, and the heat capacity at constant pressure Cp. So basic definition, Cv is the change in internal energy with respect to temperature at constant volume, while Cp is the change in enthalpy with respect to temperature at constant pressure. And using these two definitions, du is simply equal to Cv dt, and dH is equal to Cp dt. And the relationship between Cp and Cv for ideal gases is such that Cp is equal to Cv plus R. And another definition for heat capacities, since Cp is equal to Cv plus R, you can also define your heat capacity ratio such that gamma, your heat capacity ratio, is equal to Cp over Cv. Now, for ideal gases, the values of Cp and Cv can be tabulated for simple fluids, assuming they're not functions of temperature. So as such, the approximate heat capacities for ideal gases at usually a standard state, standard temperature, are the following. For monoatomic gases, example argon, helium, neon, these are your noble gases. Cv is 3 halves R, Cp is 5 halves R, and gamma is 5/3. For diatomic gases, O2 and N2, for example, and air mostly, Cv is 5 halves R, Cp is 7 halves R, and gamma is 7/5. Now, For triatomic gases, sometimes this may hold true, sometimes this may not. For example, CO2, Cv is 7 halves R, Cp is 9 halves R, gamma is 9 over 7. So as you can see, there is a pattern that we can observe. However, these are approximate constants or approximate heat capacities only, and we know from your ChemE 102 that Cp and even Cv may also be functions of temperatures using various empirical equations. So now, how do we use this in our energy balance for closed systems? So recall, energy balance for closed systems, du is equal to dq plus dw. But du is equal to Cv dt, and dw is negative p dv. Thus, Cv dt is equal to dq minus p dv. We now have an equation for the heat transfer in any closed system in terms of three intensive variables: temperature, pressure, and volume. However, we know that we can relate temperature, pressure, and volume in terms of the other two variables depending on how we want to define our system. So for example, let's say you want to express in terms of two independent variables only. Let's say first, T and V. So to express this equation in terms of temperature and volume only, we have to substitute V is equal to RT. Thus, P is equal to RT over V, and substitute this into this expression. Thus, dQ is now equal to Cv dt plus RT dV over V, and dW is equal to negative RT dV over V. And you can do the same for temperature and pressure. So for T and P, again, PV is equal to RT, V is now equal to RT over P. And substituting, you will get the following two expressions. And in terms of P and V only, T is equal to PV over R. And substituting again, you can get the following expressions. And with that, let us now proceed to the actual energy balances for closed systems for ideal gases. We can express four simple processes for ideal gas processes, namely an isochoric process, which is a process that occurs at constant volume, an isothermal process, which occurs at constant temperature, an isobaric process, which occurs at constant pressure, and an adiabatic process, which occurs at no heat transfer. So the system is perfectly insulated and there is no heat exchange between system and surroundings. So isa-isahin natin to. So for the first one, the isochoric process, the initial and final system volumes should be identical. There is no change in volume. Now, recall du is equal to dq plus dw. dw is equal to negative p dv. If the initial and final system volumes are identical, meaning v1 is equal to v2, therefore dv is equal to 0, meaning dv is 0, this dw will also be equal to 0. Thus, our energy balance will reduce to du is equal to q. And we know that du is equal to Cv dt. And assuming Cv is constant, therefore, the energy balance for an isochoric process is simply delta U is equal to Cv dt, which is also equal to Q, the heat transfer. Okay, next up is an isothermal process. For an isothermal process, the initial and final system temperatures are identical. From our energy balance equation, du is equal to dq plus dw, we know that du is a function of temperature only, such that du is equal to Cv dt. But if the initial and final system temperature are identical, T1 is equal to T2, meaning dt is equal to 0. Thus, du should also be equal to 0. Therefore, you can reduce this such that dq is equal to dw, or q is equal to negative w. So now, how do we express work in terms of our intensive variables: temperature, pressure, and volume? So recall, work is equal to negative integral of P dV from V1 to V2. We can now integrate this expression in terms of pressure. So we need to get pressure as a function of volume. And for an ideal gas, recall, PV is equal to RT. Thus, P is equal to RT over V. So we will get integral of from V1 to V2 RT over V dV. However, R, gas constant, lalabas natin. Temperature for an isothermal process is also constant. So pwede rin siyang ilabas. And we will now get W is equal to RT integral of dV over V from V1 to V2. Don't forget the negative sign. Okay. Thus, W is equal to RT ln V1 over V2. Or in terms of pressures, W is equal to RT ln P2 over P1. And to get Q, Q is just negative of W. So for an isothermal process, the magnitude of work and heat transfer should be identical. Okay, next up is an isobaric process. So for an isobaric process, the initial and final system pressures are identical, meaning P1 is equal to P2. du is Cv dt, dW is negative P dV. So based on this, we can't cancel anything. Okay, so those three terms should remain. Okay. So what to do now? So let's gawin natin. Cv dt plus P dV is equal to dQ. However, we can relate P dV in terms of temperature as well. Okay, and how do we do this? Diba? PV is equal to RT. If you take the derivative of both sides, you will get P dV, P is constant, is equal to R dt. P dV is equal to R dt. Substitute, you will get Cv dt plus R dt is equal to dQ. You can now factor out Cv plus R dt is equal to dQ. But Cv plus R, recall from an ideal gas, this is also equal to Cp, or the heat capacity at constant pressure. Thus, for an isobaric process, dQ is simply equal to Cp dt, or if you integrate both sides and assuming constant Cp, Cp delta T is equal to also delta H, which is equal to Q. So again, for an isobaric process, du is equal to dq plus dw, and Cp dt is equal to dq, which is equal to dH. And if Cp and Cv are constant, delta H is equal to Q, which is equal to Cp delta T, and delta U is equal to Cv delta T. Okay. So to get work, this is just equal to delta U minus Q, or since W is equal to negative P dV, which is also equal to negative R dt for isobaric processes. So you can also use W is equal to negative R dt. Okay? But sometimes it's mas maganda gamitin mo na lang muna to delta H and delta U, tapos pwede rin subtract na lang din. Okay, last but not least now is an adiabatic process. And for an adiabatic process, recall there is no heat transfer between the system and the surroundings, meaning dQ is now equal to 0. Okay? Thus, du is equal to dW. And based on this, Cv dt is equal to negative PdV. Now, unlike the previous three processes, recall, for an isochoric process, V1 is equal to V2. Pag isobaric, P1 is equal to P2. And kapag isothermal, T1 is equal to T2. So for these three simple processes, pag alam natin yung one of the initial states, alam natin yung isa din sa mga final states. However, for an adiabatic process, V1 is not equal to V2. T1 is not equal to T2 and P1 is not equal to P2. So there are now changes on all three intensive variables. So we now need to develop a new relationship between P, V, and T aside from the ideal gas law. Because the ideal gas law is still valid, but we now need an auxiliary equation since these are our other equations from the previous processes. So now, recall what we did earlier. We now express either P in terms of T and V, or T in terms of P and V, or V in terms of T and P. So for this case, let us express P in terms of T and V only. So CV dt is equal to negative R dt, negative RT dV over V. And doing rearranging and integrating, you can get T2 over T1 is equal to V1 over V2 raised to R over CV. So now we now have a relationship between two intensive variables, temperature and volume, in terms of other constants. And if you do this for the other scenario, so for example, T and V, you will get this, T and P, you will get this, and P and V. If you integrate both sides, all of these equations, you'll get the following expressions. So T2 over T1 is V1 over V2 raised to R over CV. T2 over T1 is P2 over P1 raised to R over CP. And P2 over P1 is equal to V1 over V2 raised to CP over CV. So we have these two relationships, and in terms of gamma, which is equal to Cp over Cv, you will now get the following relationships. So Tv raised to gamma minus 1 is constant, Tp raised to 1 minus gamma over gamma is constant, and Pv raised to gamma is constant. Typically, ito yung mas ginagamit kasi ito yung pinakamadaling tandaan. Tapos, just calculate the temperature using the ideal gas law. However, these two can also use if you can remember these two equations. Okay. So now, how do we use this? So to solve for work, simply use the energy balance equation. So delta U is equal to W, which is equal to CV dt. Or in terms of gamma, you can make the necessary derivations. Delta U is equal to W, which is equal to R delta T over gamma minus 1. Similarly, you can also get W in terms of P and V only, or in terms of T and P only. So it's up to you which one you will want to use. But typically, pinakamadali, delta U is equal to W is equal to CV dt. So just use any one of the PV gamma relationships to get temperature. So typically, gagawin mo dito, quantify all initial and final states. So quantify nyo lahat ng initial, final temperature, pressure, and volume before proceeding to the energy balance calculations. Now, generally, any thermodynamic process involving ideal gas can be classified as a polytropic process, where the polytropic process can be the following. So parang yung kanina lang, imbis na gamma, raised to delta. And W and Q can be expressed in terms of delta as well. We won't go into the derivation of this kasi medyo mahaba na, but you can do this on your own if you really want to. Okay? So now, ano yung mga values ng delta for these polytropic processes? So, for a polytropic process, if delta is equal to 0, it means you have an isobaric process. If delta is 1, okay, so for example, PV raised to delta is constant. If delta is equal to 0, therefore P raised to V raised to 0 is equal to constant. Thus, P is constant. Pero pag PV raised to 1 is constant, you have an isothermal process. And syempre, pag PV raised to gamma is constant, meaning delta is equal to gamma, you have an adiabatic process. And lastly, if delta approaches infinity, it approaches an isochoric process. Alright, so that's it for the lecture part of the ideal gas process calculations for energy balance for closed systems. The next part of the lecture will now involve actual energy balance calculations using these various PVT relationships that we have developed and derived.